Here we go. I will skip through. So I also want to talk about anticipation, but where is the right place to stand here that I can still see my laptop notes? Here. Okay. Right. So, but I want to look at the anticipation involved in complex activities. So what is video understanding? The hallmark task that we associate with video understanding is action recognition. We've all discussed a lot about action recognition now, so no need to belabor this anymore. Yes, grinding coffee. We all need more coffee in our lives, I think. So this is a little nostalgic flashback of what we used to do for action recognition. Maybe some of you still, some of the young ones probably don't recognize this. And I mean, yeah, so where has the field really gone? We've got bigger data sets, more classes now. I've made that correction live now to reflect the state of the art. But I guess 1 million videos is about right. Short, mostly trimmed videos. And yeah, single labels mostly, and deep architectures do really, really well. Same refrain, also, well, formerly poor, still somewhat not as competitive as Google type of our hardware that we're working with. So we choose to go a different route, which is to look at topics that maybe require less computational force in that sense. So we want to look at temporal sequence understanding. So it's modeling the different steps that might occur as part of a longer temporal sequence. So here in terms of grinding coffee over time, where does grinding coffee fit? It fits in the bigger picture of making coffee. And we define this complex activity as some procedural task. Doesn't have to be procedural necessarily, but it has steps or sub-activities which follow some loose ordering. So it's not a strict ordering necessarily. We find also complex activities on YouTube. It seems we find everything on YouTube. But the task that we really wanted to look at with this work here was to generalize the concept of instruction. So if I want to teach a robot how to cook now, what should we do, right? Do we have it watch all of the cooking videos that exist on YouTube, which there's really a lot of, or read all of the books, the recipe books, and then just download all of this onto your robot? Does that mean that the robot knows how to cook now? Right, so these are the main tasks that we're trying to address. And we interpreted this idea of generalization for instructional knowledge as the ability to make predictions, for one. So we define this task here as zero-shot anticipation. So the idea is that we want to be able to make predictions and also make predictions on things that we haven't seen before necessarily. So here we have, maybe we watch somebody make strawberry cream cookies, but, oh, we even have music. Let's wake up a bit. No, wrong one. I don't know how to train up the volume now. Before we had the opposite problem. Here we go. Yeah, so related tasks that conceptualize the idea that if I know how to make cookies as a whole, probably I can also make predictions for making chocolate chip cookies, even though I've only ever seen somebody make strawberry cream cookies. Probably the other way around is more likely scenario. And if we do this in a traditional supervised way, then I guess you all know we have to collect lots of training data on both classes and at test time. So this obviously scales. For recipes, I think this even might scale because there's so much cooking data out there. I'm really happy to discuss if anybody has other ideas of how we can move beyond cooking. My students are really, really tired of talking about cooking all the time. Yeah, so representative visual examples and labeling efforts, so on. So we've heard it all. So we chose to take a slightly different approach here, where we wanted to learn instructional tasks from text, purely from text, right? And then our thought was, can we transfer the knowledge that we learned only from text to video, okay? And this is also partly because we're lazy and we don't want to label videos as much as we would that text comes mostly labeled, let's say. Oops, sorry. And then in this zero-shot task, as we were talking about this zero-shot anticipation, then we want to predict the next step, having seen the video. So we take this, we take a fairly, I would say, straightforward approach in solving this task. We take a sentence encoder, parse all of the sentences in the recipes, and then learn an RNN on top of the encoded sentences, right? So this is our recipe network. And then we decode to predict the next step. And then at inference, what we want to be able to do is, of course, apply the same knowledge that we have in this recipe network and decoder, but apply it to video data. So here, what we're trying to do, so I'm also happy to discuss this afterwards, whether we've achieved this or not, is we want to separate this concept of the sequence learning of the recipes away from this visual appearance learning that we have in video, because as we all discussed all throughout the whole day, this whole appearance learning can be a very, very difficult task in itself as well. The other nice part of this type of setup, at least we feel, is that we can mix this unsupervised learning from the text with some supervised training, so that we minimize the need for labels of just purely video data. And so we think that what we're trying to do here is transfer the sequence knowledge from text to video. One last point is that we want to output our predictions here. We want to output full sentences, so in natural language. And so we want to do slightly better than just cooked chicken. We want to predict things like cooked chicken until both sides are golden brown. And our reasoning for this, even though I think it makes the tasks a lot more difficult, is that it adds a bit of richness to what we're trying to predict, for one. But also we think anyway, is that it bypasses this long tail distribution of pegging the fixed classes. So you could also argue this was just the lazy way out. Data in is sentences, data output is also going to be sentences. So we take this step-by-step approach, start off with the ingredients as the initial state, and then encode it, and then predict the next step. So given the ingredients of milk and chocolate and so on, we're going to predict boil milk in a saucepan. Then from this current state, again, encode it, and move on to predict to the next step, and so on. I should automate this. So same thing now with video. Except now with the inputs, we are getting video input. And so the key to making this work actually is the unsupervised pre-training from the recipe large recipe corpus, and then we do a little bit of supervised label data, so where we have to have corresponding text with the video for the pre-training to transfer the hidden states. So yeah, lots of... we also collected our own data set. I feel like I'm also here to pitch our own. So we scraped this tasty videos from BuzzFeed. I guess some of you guys have seen the videos before. So our data set is not so big. It's only about 3,700 videos. What we do like about it, though, is that it's they're all unique, right? So here we consider every single recipe or every single sample in the data set, every video, as a class of its own. It comes with the ingredients list and also stepwise instructions. And what we did was we annotated the temporal boundaries of each of these steps. The nice part about this data set is that, so it's all from this bird's eye view on top. And while some of you may argue that this is not reflective of real world scenarios that we might capture kitchens and environments, that's certainly true. But we think for our tasks, this is actually an advantage, because we are removing some of these difficulties that extend a bit beyond the scope of what we're trying to do. So this is what the whole system would look like once we've done the, so we start off with the ingredients. And this is our prediction. So we predict in the saucepan, bring the milk to a boil. Then we encounter this as the input. Then we predict, add the caramel sauce and stir until the chocolate is melted. So the predictions are not always, let's say, totally coherent and logical, but I would argue that at least that we've captured the gist of what's going on, let's say. Once the caramel is melted, remove from heat, then stir in the caramel sauce. So you can see there are obviously flaws of what the predictions are doing. Yeah, top with whipped cream, caramel sauce again. So this is a caramel sauce loving, and enjoy. This enjoy is maybe an asterisk beside just to inflate our statistics, because on these recipes, every single recipe ends with enjoy. Yeah, so and then if we can also compare it to ground truth, run it through all the, so here's some more visual examples where the blue is our predictions and the black is the ground truth. Yeah, so, I mean, the very obvious question is, how do we evaluate what we get as outputs, right? One is we don't know how to, we don't have good ways of evaluating with respect to natural general language. That's in a problem in itself. And then the second point is, how do we actually evaluate? Even if I get rid of all of the problems associated with BLEU scores and other automated natural language evaluation things, the different steps that we've managed to predict, right? As a whole. Some more examples. I'm happy to show these afterwards. So one nice part was actually we saw that sometimes we have completely wrong predictions, but then once it gets more visual context, it actually reverses back itself and corrects itself a little bit. So this was kind of interesting. We can compare our model based purely on text inputs versus how much the model would degrade once it encounters visual data. And there, as expected on most of these measures, we do suffer some loss. But there are other nice parts which we found kind of interesting. One is that we are able to match or outperform current video captioning systems. So this is for if I have a certain chunk of video that I've observed, and then I'm going to predict the next step. If I take the actual video from the next step and feed this through a video captioning system, our generations are on par with what these captioning systems are able to do. So you can interpret this in two ways. One is, well, captioning systems are also struggling a bit, or we're all just memorizing data set statistics. I mean, so we found this actually kind of encouraging, though, at least that we are able to match or outperform captioning systems as a whole. And where we think the improvements that we're getting currently is because of all of this pre-training. So this was our goal that we started out with, was how can we encapsulate all of this knowledge from these large-scale recipe corpus, purely language, and apply this to a visual system. So we have some various benchmarks, which for the sake of time we don't need to run through, but what we found was that our zero-shot learning setting, we do have some drops with respect to comparison to fully supervised setups, but the results are still rather encouraging given the context of the task. One way that we tackle this evaluation problem, as Jürgen has brought up, is to ask for human evaluation. And what we find is basically that our scores, the automated scores, they at least correlate in trend with what you ask a person to evaluate, with both exact matches of the next step versus, say, just a plausible next step. So to conclude, basically we've tried to show as a proof of concept that we can transfer knowledge learned from text to video with minimal amounts of labeling. We think we can gather other sorts of information, as in the various talks that we've covered today, about objects, about attributes. So recipes tend to be a good domain for this, to finding text for pre-training, right? Because there's lots of text available for recipes. But if I wanted to repeat this now on other things that tend to be underreported, for instance, common sense types of tasks for daily activities, where do we find these recipe 1 million equivalents of how to brush your teeth or how to get dressed, right? And here is a big question mark for us now, is how do we handle this robustness with respect to the video segmentation, which maybe I glossed over a little bit quickly, but when we receive steps in sentences, these are very neatly partitioned for us, right? This comes pre-segmented for free in a way. with video, how do we do that, right? Because in real life, the video comes as a stream, right? So we have to build in some form of robustness to the video segmentation itself. And this is an open problem that we haven't figured out right now. It's about to buzz. But this is my second last slide, I believe. So in terms of open questions for anticipation, the first and obvious one is about representation. Basically, what is the right way to compactly represent now large segments of video? So in our perspective of our tasks, about on the scale of hundreds of frames, where we can achieve a balance between retaining the salient visual information still, but at the same time, we can still extract the semantics over long term, right? I guess these are problems that all of us in this room are facing as well. I've had hour-long debates with my PhD student whether what we're doing here is even a real problem, especially for computer vision. This anticipation task is, if we just perfected segmentation and recognition as a whole, where does this leave for us? What is left in terms of anticipation, especially for people who work in computer vision, right? Are we not just aggregating data set statistics then? Like, what is the real underlying problem here, right? Are we looking for co-occurrence statistics? Are we trying to get into robotics of planning and logic? Like, how should we define the range or the boundaries of our problem here in vision, right? Last point that Jürgen already highlighted very well is about evaluation. What is the right way or the right ground truth for doing anticipation? Comparison of single instances, right? Because we always have some video sample that you're looking at, right? So if I make a prediction on this now, should I just compare to whatever happens next in that video clip? But this video clip is just one single instance, right? But if I just take purely plausible outcomes, plausible is just your data set statistics that you're averaging over that whole data set, right? So what's the right way to evaluate? So I'm very happy to discuss and hear ideas about if you have thoughts on these things.
Thank you very much.
Yeah, so today's task.